So this is a rant about asymptotes. You've seen asymptotes already a lot. The classic case of an asymptote would be the function y equals 1 over x, which of course, just even before we can proceed, we need to write down the fact that we're not going to divide by 0. Because mathematics is true. You can't go writing down stuff that's wrong. Then the mathematics breaks down and you're just like drawing shapes. Even that might be mathematics, but in this case, of course, x can't be 0. Now in this case, where we're dividing by 0, and we can't factor or cancel it out, right? Like in this case, our function isn't set up in a way that we can cleverly cancel it. Like, look, if this were our function, we can be really clever and cancel the x's and just get 1. So we can't, and then we could remove this singularity. It'd be removable, but it's not removable. So we can't factor or cancel it. That is, we can't remove the singularity. Okay, I'm just saying. So what does that mean? A removable singularity, where you can factor and cancel, just looks like that. Removable, that looks like a hole. It's just like a little hole in the graph. And when you factor out the hole, you basically fill it in. See, look, I removed it. It's so easy. Okay. If it were only that easy to do it in your formulas, but it's not too much harder when it works. But it's easy to see on the graph. So when you're dividing by 0, that's going to give you a vertical asymptote. A vertical asymptote is the kind of singularity that's like this. In this case, the graph of 1 over x, this is y equals 1 over x, looks like this. And of course, as we saw earlier in the semester, as you get closer and closer to 0, the point of singularity, it's almost like there's a force at that y-axis, x equals 0. It's almost like there's a force that's pushing back at the graph. Like as you're moving along the x-axis, your function wants to go to the y-axis and cross it. But the y-axis is pushing back with like a force field. So it's like bending, it's pushing towards it. It wants to cross that axis, but the axis is pushing back. So forever, no matter how high you go, it'll get closer and closer and closer. But it'll never cross, in this case, it'll never cross the y-axis. And same here. You can go closer and closer and closer and closer, and you will never cross the y-axis because there's an asymptote there. You can't let x be 0. That's the force. The force that's pushing back is the fact that you can't divide by 0 at that point. It's creating like a force that's pushing against those functions. That's the way I'm seeing that. It wants to cross the y-axis, but it can't. So dividing by 0 gives you vertical asymptotes. Okay? So that's the graph and the asymptotes there. Now I know you know that. BTW, asymptote, is a Greek word, and it means something like they do not meet. So that it's an asymptote. It means they do not meet, and what's implied isn't just that they don't meet, but that they get closer and closer. Okay, we're used to this kind of idea by now in the semester. But there are other kinds of asymptotes. For instance, the graph of y equals the natural log of x. It passes through, at 1, it's 0. And for any log of 1 is 0. But because the domain of the natural log has to be, it doesn't even include 0. The natural log of 0 can't be, that's not defined. X has to be greater. So again, because X, the restriction on X forces the function not to be able to ever get to that line. In this case, the logarithm's decreasing. Well, it's increasing, but as you go towards 0, it's decreasing, and the y-axis, the asymptote, is pushing back this vertical asymptote. In this case, it's the y-axis at x equals 0, is pushing back on the logarithm function. So as it tries to go towards the y-axis, it's just like pushing back, and it just gets closer and closer, but it can't ever get there. Okay? So that's another example. So if you see dividing by 0, where you can't cancel it, you can't remove the singularity, if you see logarithms anywhere in there, you know you might be worried about these kinds of asymptotes. The function introduces the asymptote. The force field that's being produced is being produced by the function and its domain. Because remember, the function isn't just a formula. A function is a formula like y equals f of x, a formula or some other kind of relation. Maybe it's a table or a graph, and a domain. You have to specify the domain. The function, just that, isn't a function. That's just a formula. You don't know enough about it to have a function until you see that. Which x values does it work for? Cool? So in any event, all right. Now let's look at the problem. The problem is saying that we have a function that is like this. Well, let's just look at x to the 3/2 before we go further. Actually, let's look at x to the 1/2. What does x to the 1/2 look like? It's the square root function. It looks like this. The square root function is the positive square root, and its domain is x greater than or equal to 0. Square root of 0 totally makes sense. 0 squared equals 0. Square root of 0 is 0. But the square root of a negative number doesn't make sense. But also notice that there's not an asymptote involved yet. Not right here. There's not an asymptote. There's literally, the function stops there. But it's not a force field pushing it away from the line. That's just the end of the domain. Over here, that's not part of the domain. Let's just go ahead and make it a dotted line so you don't get confused and think it's in the domain. Okay, now I'm getting to the particular problem, but I just want to point out dividing by 0 where you can't cancel it, logarithms, these are functions, simple basic functions where you know the graph has an asymptote. And if those functions show up inside more complicated expressions, wherever those functions show up, if you see logarithms, if you see reciprocals where you could be dividing by 0, in all of those cases, you're going to end up having an asymptote somewhere in your function. Unless somehow the function magically gets rid of those in some really, in a very clever way, that's not usually the case. So starting to address the problem that you asked about, that problem doesn't have logarithms or dividing by 0 involved. I don't believe there's a reciprocal. So right off the bat, I don't see either of the two templates for an asymptote. What I see is y equals x to the 3/2 in this problem. All right. Well, you could rewrite this if you wanted to see it kind of more correctly as using exponent rules this way. And of course, that's x cubed, the square root of x. Cool? The square root of x cubed. I don't know exactly what this looks like on a graph. It doesn't matter right now because all we need to know is this. The function here that's going to get funky is this. If x is equal to 0, let's think about this. If x is positive, then x cubed is positive. And so that case is cool. positive stuff can go inside the square root symbol. If x is 0, well then the cube root of x cubed is 0, and 0 can also go inside the square root. On the other hand, if x is a negative number, then x cubed, because cubes, odd powers don't cancel the minus sign. And x cubed is also a negative number. So these two cases were cool. You could put, in both these cases, you could have a square root of those numbers. But if x is negative, x cubed is negative, and that means that you have the square root of a negative number. Put little quotes around that. And that's not good. We're not using imaginary numbers in this calculus. This is the calculus of real numbers. So that's not acceptable. Anything that leads to a square root of a negative number falls outside of the domain of this as a function that's based around real numbers. Cool? The graph of this function is not going to look very much different from the graph of this function in terms of its x-axis. It's got the same domain. Whatever this function looks like, something like, I don't know what, but I'm guessing it looks something like this. I don't know. I really don't know what it looks like. I'll just put a squiggle with a question mark. But whatever that function looks like, it's got the same domain. And notice that x can get to 0. So it's not going to have an asymptote. The square root function doesn't introduce an asymptote, but rather it introduces a chopping off of the domain. You only get to use half the numbers, half the number line. Cool? So now let's reshare. Would you mind resharing that problem, please? Thank you. Okay, so now let's look at the problem. At a equals -4, notice that x plus 4 to the 3/2 power, does that break the domain of something to the 3/2 power? If you put -4 plus 4 equals 0 inside this, is that going to change? Is that going to break the function? It doesn't even cause the function to have a, it doesn't even cause the function to have any issue there as far as its limits go. And so at that value, a equals -4, I don't see that there is an asymptote. Now, however, let's check out and see if there could be an asymptote at a different x value. What do you think? Looking at what I've just described, is there any aspect of the square root of the, or rather the x of the 3/2 power function? Is there any aspect of this that should break for some number? Should you be able to plug in a value of x into that equation on the problem, f of x, that actually gives an asymptote instead of just making it suddenly does not exist scenario? Or sorry, not does not exist, but rather that the function is undefined? I'm not seeing that a square root symbol in there, since there's no reciprocals, there's no logarithms. I'm not seeing that there's anything that should be causing an asymptote to appear. So my feeling is that there could not be an asymptote because there is no basic function involved that introduces one. You can spot it by looking at the formula. See, there's no logarithms and no reciprocals. Now, if that were in -3/2 power, that's a reciprocal, and suddenly we would have an issue. Let's see. So now, is there a removable discontinuity at x equals -4? Is that discontinuous at x equals -4? Certainly, it is not left continuous because the left side of that function, there's the domain, there's no, you can't use the left side. You can't approach from the left. But it is continuous from the right. And so I don't believe there's a discontinuity there at all. X equals -4, what's wrong with that value? It's totally fine. 0 to the 3/2 power is 0. And then at the bottom, it says, no, there is an asymptote at f of x equals -4. And in this case, I ask once again, how could f of x equal -4, right? F of x is equal to the square root of something. And as long as this makes sense, the way the square root function is defined as a function is that it's the positive square root. How could the positive square root equal -4, right? Because that has to be something real. It can't be imaginary. How could the positive root, like what could that be? So that last one doesn't even make sense. F of x equals -4, what? That can't equal -4. It's always greater than or equal to 0. It's the positive square root function. So I think that covers all of the bullet points for that problem. Answering it is just a matter almost of spotting it, looking at it and seeing that there's no reciprocal or no logarithm. But you wouldn't know that without me telling you that. That's not obvious. That's a matter of intuition and kind of experience that I'm trying to pass on to you. The thing that introduced the asymptote would be a function that's inside the composition. And you do have to be careful about that to work it out the way I did in that case. So I believe that that's the answer for that one. Cool? Now let me say just a little more. About asymptotes, and then please let me know if that is useful too in the chat. I just want to say one more thing. So what we've just looked at is vertical asymptotes. Vertical means like up and down, right? So we just looked at vertical asymptotes. And what do these usually mean? Dividing by 0. Or they mean that you have some logarithms involved. Or other functions that have, there's other functions in existence with vertical asymptote. Like some trig functions have vertical asymptotes, like y equals tangent of x. If you look at the graph of that, you see vertical asymptotes. But in the end, that just comes down to dividing by 0. So it's a little misleading what I'm saying, but anyway, if you see functions that have asymptotes, then you're inside a function, then you can guess there will be asymptotes. On the other hand, other kinds of asymptotes are horizontal asymptotes. And you've seen these already as well. And you can even have diagonal or slant asymptotes. These we're going to not talk about for now. This rant, I just wanted to mention horizontal asymptotes as well. What does a horizontal asymptote mean? Well, let's look again at the function y equals 1 over x, where x can't be 0, and let's look at its graph. Now, we already discussed how there is a vertical asymptote at x equals 0. But what about if you go out that way? If you follow out that way to infinity, you know from your study of limits that the limit as x approaches infinity of 1 over x is 0. But you can also see, since all of the x values are positive, that these y values will always be positive. That is, they'll always be above the x-axis. That line never crosses the x-axis. They don't meet. In this case, the x-axis serves as a horizontal asymptote for this function. And similarly, going out in this direction, this function will never cross the x-axis, but will get ever closer to it as you go out to infinity in both directions. You all buy that? And so while vertical asymptotes represent things that feel kind of like a little bit like the functions are breaking, like dividing by 0 and things like that, they represent values that you can't put into the function. In fact, horizontal asymptotes they're good. I mean, they're all good. there's no bad math objects, but horizontal asymptotes represent limits. They represent limits as x approaches plus or minus infinity, when those limits exist. So these are numbers. Horizontal asymptotes aren't lines that you can't reach. They're actually values. They are finite y values. A horizontal asymptote on a graph looks like this. Maybe your function's like, and there's some value here, let's say L. The function grows ever closer to as x goes to infinity. That would represent a horizontal asymptote. Now, I just want to make one tiny little point. Asymptotes don't necessarily have to, a horizontal asymptote and vertical, they don't necessarily have to never touch it. It's possible that this could happen. It's possible you could get it could cross it some. It could cross it some, but the point is that it never diverges from it again. It always stays getting closer and closer on average to that asymptote. Notice my drawing makes it look like the ripples are getting smaller and smaller and smaller as you go on out. So on average, it still is never exceeding that limit anymore. But generally, though, we do actually mean in Calculus 1, we do actually mean that they don't actually meet. I just want to put that factoid in. And that is the end of my rant about asymptotes.